mute their phones. And I'd love questions, but I guess since we have quite a few people, we probably should wait till the end. And the other warning is this is the first time for this revised version. And as you probably noticed, there's quite a few slides. I'm going to try to go quickly, but if you feel you have to drop out at the end before I'm done, no big deal. Feel free to email me any questions if you don't get a chance to ask them. This is just a little weather trivia that you'll probably never use, but July is the anniversary of a tornado that occurred back in 1985 north of Denver, and it was actually the first non-supercell tornado documented with Doppler radar, and we'll show you a few conclusions from that study that we did on that storm. So again, this module is a remake. What I'm trying to do here is, there's been a lot of research done, especially by the sport folks, about lightning and total lightning and severe weather, especially in-cloud lightning, that is. The thing about non-supercell tornadoes is they're very much tied to updraft strength, and since that is also a key correlation with in-cloud lightning, it seemed that there could be a relation there to non-supercell tornadoes, and they're hard to warn for, so that's what we've been looking for here. It is, at best, a tool that you can add to the problem. So we'll spend a little bit of time on this first study because it's really intriguing, and it's a very comprehensive study, a lot like what we did back in 1985. And then we have some other cases. Actually, we just added yet another case from New Orleans last Friday, I believe it was, and then suggested ways. Well, I don't have to talk about this much. The thing about when we originally started doing this, we were thinking GLM only, but of course, GLM has taken a while. In fact, it's not fully operational yet, but so there's Earth Networks Total Lightning, which is a ground-based system. So we'll actually show a little bit of that as well in some comparisons. Obviously, there's a lot, and you've all taken the SAT-FCG course, so you know a lot about, and our quick guides and quick briefs available on lightning to refresh yourselves if you need them. What about a non-supercell tornado? So the key to this, in many ways like a water spout, which is why they often refer to as land spouts, they develop really from low levels upward. So often, and not always though, we're finding out, but there can be no mid-level precursor rotation. So we have seen cases though where there's some mid-level rotation. I don't know if it has anything to do at all with the actual tornado though, but in a supercell, obviously that's the key to warning. We look for that mesocyclone. Well, there is no real mesocyclone signature, so that's what makes these things so hard to warn for. And the other issue, of course, if there is a signal, it'd be down low, and so the radar beam may overshoot it, and the diameter of the rotation is going to be quite small, so that makes it even harder. Generally, what we found out here is that, if you're more than about 30 miles away, you're probably not going to be able to detect some of these low-level signals. So again, the connection, as I mentioned earlier, the thing about the non, and we'll go through a little schematic here in a second, but you start with some low-level rotation, say along a boundary, updraft from a growing cell happens to position itself over that rotation. The updraft strengthens, it then stretches that low-level rotation upwards, and you may get a tornado. So a boundary is a key. That's one of the things where often a key anyways for getting the source of this low-level rotation. So this is Ray Brady and I think Ray is still a forecaster in Binghamton, I believe, in New York. We came up with this based on that 26 July 1985 tornado. And the idea is that we will often see, if you're close enough to the radar, circulations along a boundary without any clouds present. So if a cloud might develop along the boundary, right, because you do have that forcing. So if one of these happens to position itself over one of these circulations and starts to grow, then it starts to stretch that vertically, and you conceivably could get a tornado out of that. Now, we often think of these as pretty weak, but we've seen them as high as some areas of EF3 damage out here. And the thing about, I think one of the reasons suspect that one of the reasons that we often don't get a lot of damage out of some of these is that their diameter is really small. We had one that was pretty close to Boulder. I did a storm survey of it. The damage swath in the grasses were about 20 feet wide, but I think the winds within that little damage, within that rotation, can be pretty strong. So the issue is it probably has less chance of hitting something, obviously. But I would not want to see these go through a mobile home park, for instance, and I would expect significant damage would be possible. So this is, I want to give credit also, shortly after we came up with our paper, actually within a couple of months, a much more complete study, of course, by Roger Wakamoto, using this data from a field program called Cindy, I believe it was in 1987 out here. They use many cases. Now, the one thing that's kind of curious about their schematic is that it seems to show these things developing before the cloud gets very big, but we found that generally it grows larger than that. And if it were to be this small, then total lightning would probably be useless because, of course, the key is you have to have lightning and the cloud will have to get above the freezing level. The term, by the way, landspout, as far as I can tell, was first used by Howie in the 14th Severe Local Storms Conference. He didn't have any real data on it, but he noticed this other type of tornado. All right, so let's first look at this one from 2013, and it's kind of interesting because Jeffrey Stano from Sport had come out to talk to the Boulder WFO, and we were prototyping GLM potential products by using the Colorado LMA network. So he talked to us about a bunch of things, and I was sitting there listening to him and thought, well, gee, I wonder, he showed some of the usual hail versus lightning jump, etc., and I was thinking maybe a non-supercell tornado could be related to this. And sure enough, within a couple of months after his presentation, we had this event. I happened to be working a shift, and it was fascinating to watch this develop, and we'll show you this in a moment here. And there were actually two cells, which was kind of interesting. One formed a tornado and one did not. So we're able to compare the two. And this actually was right at the airport. We'll show you a map in a second. Here's what our typical land spouts look like. Mostly dust, but that's not always the case, but a funnel. And this particular storm, I don't know if you've been, I'm sure many of you have been to the airport. This is the main terminal building, or the main where you have to go through security, and then there's Terminal A and Terminal B. And you can see this thing was heading right for the airport. It crossed one of the runways. We had a site here at 109 miles an hour. Just kind of fun. But what happened? So they eventually, we were in contact with the airport, and eventually they decided that they needed to take some action. And they actually, this is the middle of the day, they actually were able to empty all the concourses, except apparently Howie was there running around from window to window. But where did everybody go? If you've been to the airport, well, they went to the train tunnels for the most part. And there's a picture that's kind of cool. The fascinating thing to me about all this is that it took only about 80 minutes for them to recover from this event, which I thought was pretty amazing. So this happened in the middle of about 3 o'clock in the afternoon. So here's the sounding for the day. Typical of a non-supercell situation, we have a almost adiabatic lapse rate, pretty steep. Notice again, the freezing level here is pretty high, but our clouds get pretty high. We start fairly high cloud base. Not much shear at all, although there is some here at higher levels, and there was actually a severe thunderstorm watch for farther east. And enough to support perhaps some mid-level rotation, which we'll see in a second. So what I'm going to show you here for this event, and this was our display of the Colorado LMA, and we're going to be looking at this area right here near DIA, and these two storms shown by the arrow. And I've blown up the area of DIA, and what we're plotting here is called source points. You can kind of think of them, and again, there's a land base, so it's not directly related to what we see with the GLM, which is taking a picture essentially, but sort of like a pulse in the GLM terminology. So initially we have a couple of cells. This is composite reflectivity developing, and then one of the cells start to show some action. We're going to update this every 10 minutes. And notice the southern one really starts going stronger. The northern one begins, and the northern one rather quickly takes over and becomes a really sharp increase here. Now, the tornado hasn't formed yet. It's still, we're talking about 2022. I think we're going to get to the tornado here in a bit. Still growing, and finally at 2021, we confirmed the tornado. Now, we were convinced, of course, we're very close to the radar, so we really didn't need lightning at all in this case. Here's a terminal Doppler from the terminal Doppler radar, and you can see there's obviously a beautiful signature and a nice little hook here. But it was nice to be so close and to be able to document what all happened and to know when it started. So we'll use all that information here to basically try to do the same thing we did back in 1985 and compare the two cells. So here's what I'm plotting here, and it's a time height, a time diagram going this way, the tornado's here, and then I'm plotting the number of sources here. So one thing you can see right away is that the tornadic cell, this northern one, has about twice the amount of activity as the southern one, which didn't. So that's kind of good. The other thing, there is a ramp up that occurs. It's actually right at the tornado time, so not exactly a lot of precursor signal there. But there are these weird dropouts that occur, and Jeffrey looked at the data in detail and found that there were some dropouts in some of the sensors, so we really can't believe those particular dropouts in this case. So let's now compare this with a couple of profiles of reflectivity and then velocity for this cell. So we see a pretty sharp increase initially here, and that's when the cell is growing. Now, I use some other radar data to get farther away, but this is still as high as we can get with this particular storm. But you can see that, but unlike some of in fact, this is a little more confusing than that Erie storm we studied in '85, and I think some of the ones that Roger and Jim Wilson studied in their study as well, and that this cell hangs around a while before it actually produces the tornado. And there's a steadiness in the lightning, and then this jump at the end. And if you compare it then to the velocity, I think this is kind of interesting. Initially, the cell is growing, and we see this low-level circulation that pre-existed. This is a gate-to-gate, or this is maximum rotational shear in knots. It doesn't not necessarily at all gate-to-gate. But then what you see is as we get closer to the time of the tornado, we have a rapid increase in the vertical of this low-level circulation, building up to this rotational signal here, about 100 knots in this case. How about the southern cell? We get an initial lightning increase as well, but after that, notice it stays pretty steady. In fact, even goes down, and we don't see much of a change in the reflectivity structure. And in terms of velocity, is that business of a bit of a mid-level rotation, but generally none of that stretching that we saw. And in terms of what must have been going on with the updraft, we see with the total lightning, not much of a change. So I found this encouraging in that the one that produced the tornado had the big increase, had more total lightning, and a lightning jump of sorts did occur. The downside is it was very close to the time of the tornado, so it wasn't exactly giving you much precursor, but at least in terms of comparing the two cells, there was something there, I thought. So shortly after this, another Rob Cox alerted us to a case that occurred up near his WFO, and he was also using the Colorado LMA, and in his AWIPS, he had it mapped to a sort of GLM light display, and we'll show you that in a second. So this was his tornado, again, mostly dust, pretty close to the radar. Dan and I went up there and looked at the data in detail with Rob, and we could not find any signal like we did for the one in Colorado. So in this case, there wasn't a lot of help from the radar. But there was a boundary, as Rob indicated here, and kind of a colliding boundary, a pre-existing boundary with an outflow boundary. Often that's what happens to get things really going. And here's what he saw. And you can see in this case, again, we're plotting number of sources, which is different from what the product is now. But you did see this lightning increase, lightning jump. And For his case, he suggested that it was maybe 10 to 15 minutes prior to when the tornado developed. So this was also, again, pretty good. I didn't show you the sounding, but like the Denver one, very steep lapse rates. So this is about where we ended with the previous version of this training. Since then, Dan and I have been gathering many cases, some sent to us, some we've noticed, and we've had help from, of course, Kyle here to help us get some of the lightning data, and then more lately, we've looked at some of the things on AWIP. So I'll show you a series of these. We'll start with this one in last year, a fascinating Iowa outbreak. This is kind of something Kyle put together, and you can see all the lightning that happened. And these are all the tornado tracks. Now, some of these initial tracks up here, there's almost no lightning with them. So we didn't look at those. What we did, we looked at one near Bondurant and then one of these tornadoes near Monroe. After this point, these storms actually become more supercellular, so we did not examine those. So we'll show you these couple. And then just a quick look at the satellite. Here's the essentially the line the boundary that we had, kind of a westerly flow. I don't know if you'd call it, I guess, a cool front, maybe, but it's quite warm behind it, and things, as you can see, really get going ahead of it. So southeast winds opposing more westerly winds. Not always the case to get a non-supercell. Sometimes we have more stationary boundaries. This was a little different. So here's the Bondurant tornado, and just showing you the plots. In this case, we're looking at essentially GLM flashes, total flashes per minute. So we'll show you a more parameter that you get, flash extent density, here in a second. But what you can see is that, again, there's a ramp up, but it is really sharp increase comes during the tornado itself. There is a nice increase ahead of it, but really the sharpest during the tornado. The one for Monroe was more enticing, if you will. We see this fairly steady, and then a really nice lightning increase occurring beginning about maybe 10 minutes before the tornado here, and then peaking a few minutes before the observed tornado. Now, we should note one of the difficulties with doing all this is that you have to assume, and sometimes we have video to back this up, that you have an accurate time of when the tornado began, and that can be a limitation. And maybe it was earlier than this, maybe it was actually a little later. So that's a part of the inexactness here. So that was kind of cool. There's a case that occurred this year that was pretty interesting out near the eastern Colorado border. These were all designated, at least by the chasers, landspouts, and it looked like the shear was pretty weak on this day. So, but several of them. This is out near Goodland is right here. So we're looking kind of to northwest of Goodland. This is the Colorado-Kansas border. So we'll look at a few of these, or a couple of pictures. This is one near Goodland, kind of typical. This is quite an interesting picture near the state line. And what was neat about this boundary, which was this is the Meso-West plot here on the right, but it's notice how it kind of runs in this direction, but what we have is winds. They're not a direct opposition, and often we found some of the most effective boundaries to produce these little low-level circulations or shearing vortices, if you will, along the boundary, are ones where the winds kind of come at an angle. And we found this one of the most impressive outbreaks of tornadoes in Denver metro history occurred in 15 June 1988 with a similar boundary that was then increased when two outflow boundaries happened intersected. It was a fascinating outbreak, and there's several articles written on that. And this is the type of boundary that was, and this boundary was obvious. There were probably many other circulations on this day that didn't actually form a tornado. So here's a little look at a loop here, and I think Dan told me I need to increase the loop speed. I don't know if that's anything. I'm not sure. Oh. Animation, there we go. Okay, so we're going to look at this first cell. This is the cleanest of them, this one over here. And this is so what you'd probably be looking at generally would be flash extent density. What we're going to show you is how you can also, if you wish, and it can be clunky, I'll admit, but there is a tool on AWIPS called the tracking meteogram tool. So we applied that tool around this cell. One thing that's nice about non-supercell tornadoes is they won't normally move very much, so if you were able to circle this area, you would probably get most of the lightning. And what we're showing over here is the flash extent density, and so that is the number of flashes within a grid box, not the total number of flashes, because you actually would be double counting some, because they may go across the 8 by 8 kilometer grid boxes. In this case, there isn't a lot of lightning with this first storm, so these numbers are pretty low over here. But we do see an increase that occurs, about, in this case, 15 minutes prior to tornado. But then it kind of goes down, so that's a little hard to explain. If we look at the next, here's a comparison. Actually, this is Earth Networks only here. So we have Earth Networks data that we just recently got. So here's that same tornado. So they're measuring, it's a ground-based network versus the one from above. So each has their own issues at times. But this is cloud to ground here, which we would not expect to have any real correlation with the tornado, because that often occurs when we have a downdraft wind precip to the ground. But here's their measure of in-cloud. Now, one thing that's nice about the Earth Networks, you can actually separate the in-cloud from the cloud to ground, which you cannot do, of course, with the GLM. It's a total lightning. But often with these non-supercell events, the total lightning initially, a lot of it will be in cloud. But notice there is a nice ramp up here, better than what we saw with the GLM that occurred prior to this non-supercell tornado. We also then look at this next one, and this is far more confusing. Here's the GLM, peaks way early, and then kind of just flounders along. I don't know what to say about that, except that obviously signals can be mixed at times. Then this is a difficulty. This next area where 2 to 3 tornadoes were produced was in this line, so we kind of did the whole area, and what we got is a deal like this. 3 tornadoes occur, shown by these yellow lines, and you can see, well, one of them not much happening. For this one, a pretty decent ramp up, maybe a little bit of a ramp up here. This is actually the total lightning down here. I'm looking at a couple of other things, which may be products in the future, pulse energy, and then this is actually Earth Networks again. I'm sorry, this is the Earth Networks, and 1 minute cloud flashes. So that would be one more. But this total lightning can be compared more with the GLM, and in this case, it's probably one of the worst comparisons we actually saw for all the ones we did. And you can see there's, we have to get the experts to give us a little more opinion on what is going on here, but maybe the way we were looking at such a group of cells made it a little more confusing in this case. Iowa tornadoes, again, Iowa hit with a very interesting outbreak beneath the upper level low on 29 May. This is one, we'll look at this. There were 2 tornadoes that we wanted to look at. These others, again, we were not sure that they were non-supercells. This first one was a brief tornado, and there was actually no lightning with it. So that's one of the issues of it. And we found that people in the southeast have told us, well, we don't get storms that develop as deep as out there, and they seem to have already produced a tornado. Well, then this obviously won't work. But this one was interesting here. Lived for a while. There's a photo of it over there. And we will animate this even. Oh, it is going fast. So again, this what we're looking at here is the flash extent density, total optical energy. These are some other things, just kind of experimenting to see what might work, and then average flash area. And again, the meteogram tool, and then this in here is the cloud phase distinction, where you can see the phase change in the cloud from liquid to ice. So looking at this, and again, I've highlighted the flash extent density here. What we saw in this case was, again, a pretty good ramp up, and then it sort of steadied. There were some other interesting looking signals, perhaps, in some of these other parameters that you may get eventually. When we looked at Earth Networks, the tornado is actually starts out in this area here, so that data for this day cut off, but we do see a pretty interesting little ramp up. Again, a little more solid looking perhaps than what we saw at the GLM. Here's another one that was very close to what we looked at earlier with the network. That was out here, remember, on I think it was in June 8th. this one in 5 July, and again, these are non-supercell tornadoes. Again, a boundary similar to what we saw there, not quite as strong, but a sounding that did not have much shear and pretty unstable. In this case, again, we're focusing at first on this storm, and you can see just looking again at the flash extent density, this would be a product, maybe you'd just be looking at it visually without this mediagram tool, but you can see there's a pretty good increase. And one thing we should mention, in this case, we adjusted the scale from the default. For some of these non-supercell tornado cases, there may not be a lot of lightning, and you may want to adjust it to towards lower levels to get more distinction. I'll go back there just once. The other thing we noticed, the total optical energy sometimes seem to correlate pretty well as well. So here's the GLM products for the total optical energy down here, and then the flash extent density on the top. And what we see is a kind of a ramp up a little bit in the first case for the first tornado, then it kind of holds steady, and it's kind of a mixed signal, I would say, but a general increase was happening. If we look at one of the other tornadoes, this was back in the one in New Mexico. I'll pick up the speed a little bit here. Again, we're looking, and it's a little more confusing because we have a lot of other stuff going on, and in this case, here's what we got. And I would say, again, total optical energy down here, and that almost looked like a better correlation than what we saw with the flash extent density up here. This yellow line being the tornado time. The last case here is from New Orleans. This is very recent, and often waterspouts may not have much lightning activity, but we noticed this one had quite a bit, so we took a peek at it, and not sure the exact times of these photos, but based on the Doppler, based on the rotation signature, this is from MRMS. There's pretty good rotation in here, so, and it looks like it nearly came on shore. Maybe it almost did. So these are pretty good cells. Some of the earlier ones also had a little bit of rotation, but apparently no tornado with them. So here's the signal or the behavior of the lightning for this particular case. Now in this case, I think there is pretty good agreement between the GLM here and the Earth networks. Again, we're looking at the total lightning product for both of these. Now remember that they're not measuring the same thing. Our best interpretation of Earth networks, what they call total lightning, would actually be groups in the terminology of GLM. So the numbers are going to be higher for Earth networks, but the behavior looks pretty similar. So we do see this nice ramp up here. Obviously, this is a lot stronger ramp up, so this cell was still growing after the beginning of the tornado, which was right here. So some signal, but obviously, if this had occurred before, this would be much more impressive. So what do we conclude from all this? This is obviously not something you would just say, wow, well, let's look at this and issue our non-supercell tornado warnings. But I sort of think of this maybe as, you're concentrating on a boundary, say you've seen it the day, it's pretty unstable, maybe there'll be something along it. You start to see one of the cells having a very rapid increase perhaps in total lightning. If other things may agree with it, maybe you even get a call. Somebody says, I see, I think I see a funnel cloud or a tornado has grown up here. Instead of, in the old days, we probably, half of these calls, we'd say, oh, come on, there's nothing out there. We'd look at our radar. Well, now maybe, you have more situational awareness. You might go ahead and use this to help you convince yourself that in fact, it is real. Obviously, we're trying to put together as many cases as we can from different areas to see what sort of magnitude we get of this and how consistent the signal is. And you've seen that there's obviously some inconsistency here. So that's all I had.
Hey, Ed, appreciate the presentation. Pretty interesting stuff, and I like that. Some very recent cases. One of the things that I've been having trouble with is determining what classifies as a lightning jump. Whether it happens later on down the road within the storm's development stage, or anything just initially? Do you know of any guidance that might help?
Well, yeah. So I specifically didn't. I know that when sport has talked about this, they talked about certain levels that define a lightning jump, and I didn't. I'm just more looking for a lightning increase, I guess. And as you saw, in terms of when it, obviously I was hoping that in terms of having value for this, what we'd see is this lightning increase, and we did see it obviously in some of these cases before the tornado. There will also be increases in other cells. What we're sort of looking for, I guess, if you're in operations, would be, say you were looking at that flash extent density graphic, you'd be looking for maybe a maximum in a certain area with a certain cell, and see if that might be the one. But so no, I'm not actually applying a strict definition here, and probably I don't know in terms of this particular application if that's necessarily that important. But I know sport has talked about certain sigma levels and stuff as to what defines a lightning jump.
Hi, this is Kyle.
I don't know if that helps at all, but
Hi,
Yeah, appreciate the insight.
Hi, this is Kyle at Sierra. Can you hear me?
yeah.
I just wanted to make a comment on that. In addition to looking for a large jump in lightning, it's also important to look at the actual absolute value. Because if there's not a lot of lightning, that jump may be not as meaningful. And what exactly absolute value is appropriate may have a regional dependence. That's a topic that still needs more research, but I just wanted to put that out there.
Yeah, Kyle, and Kyle is the one who has helped us a lot with interpreting and plotting some of these figures. A lot of some of the storms we looked at, though, Kyle, didn't have very much lightning at all. So, the amount of increase relative to, it wasn't much compared to the total amount of lightning that, other storms have. But there was an increase in what there was. But we even examined, I didn't show one storm we had near Lubbock that maybe had like 3 flashes, which was pretty, Anybody else? I guess I was wondering, does everybody have the GLM at this point?
Yeah, the Cleveland office has all the experimental products as well.
Okay.
Yes, Huntsville does.
And I know Boulder does, of course, but
Grand Forks, we still only have the flash extent density.
yeah. Now, do people use both Earth Networks and GLM? Have you found, or are forecasters showing a preference for one over the other? Or
We've been teaching and really driving hard to use both whenever you're trying to look for lightning. To use the kind of ground-based and space-based network.
Anybody else have any, or just, if you see a case, by the way, and wish to share it with us, let us know. We have AWRIPS up in Fort Collins that we can save data for.
Ed, this is Dan. I saw a recent blog post from Chris White at Huntsville that was very nice on looking at the GLM for assisting in issuing a warning. And Chris, you said something in that blog about 2 sigma, kind of as a way of looking at a lightning jump. Can you tell us how you got to that and give us a little info on that?
Yeah, hey. Thanks. There was a recent case where a forecaster on shift did use the GLM as a piece of evidence about issuing a warning. So the 2 sigma thing, that came in hindsight. When I went back and looked at the data, he certainly wasn't, sitting there statistically doing all this. That would be quite rigorous. You can, you could use something like the tracking meteogram tool to kind of count out these values as you're going along. But still, there's a lot of math involved. Incidentally, we have a Hauling Scholar student here this summer who's working on this kind of stuff, and we had Chris Schultz down here, and he helped us throw together a little Excel spreadsheet, essentially, which does this continuous count of the GLM signal levels, which is dependent upon it was based on the 1 minute FED data, and then we compute averages for those going over a period of 10 minutes, and then you have to compute standard deviation and all this sort of stuff. And so in hindsight, when I went back and looked at that case, it did constitute a statistical jump per Chris Schultz's methodology. Now, it might not have been entirely intuitive at the time because these values were still relatively low. But, someone made a comment earlier about, the absolute value may ultimately matter, and indeed it may. But this wasn't a tornado case. This was just a severe wind case. But with that statistical methodology, you can get a jump from relatively low values. So let's say your values are kind of just moving along, say, between something like 4 and 8 flashes per minute, and then the next flash comes in and it's 16. Well, then by that methodology, you would have a statistical jump. You'd still have a fairly low number, only 16 flashes, but based on that 2 signal level, it would qualify as a jump based on his methodology. So anyway, that's what the case that I read up had to do with. The forecaster at the time, it was one of those situations, and we've used the data like that here before. Historically, really the LMA data when we had it in operations here. Is that it serves as one additional piece of evidence. So if a forecaster, say, is on the verge of issuing a warning, or they're pretty close, and then all of a sudden you get a sudden increase in the lightning data, that suggests that, well, then you have a significant increase in your updraft strength or updraft mixed phase volume, and that would indicate that perhaps the cell is about to produce severe weather, so it can help tip the scales in favor of issuing a warning. Hopefully that described it.
Yeah, thanks, Chris. Anybody else have any thoughts?
Hey Ed, this is Kyle at Sear. I have just one more comment. The key physical assumption here is that there's a strong relationship between the presence of lightning and an updraft, and most of the time that's true, but if there's anvil crawling lightning or in the stratiform areas, that assumption might start to break down. So when we find cases that are harder to explain, I would point the finger at that, because I found that's kind of a complicating factor in interpreting lightning time series. Thanks.
Yeah, thinking about that, that's a very good comment, because I think that one case I showed where we had three cells together, likely there was a lot of anvil activity at that point. And so maybe that's why that whole thing looks so confusing. A lot of times with non-supercell tornadoes, they tend to occur, but not always, early on in the life cycle, so that may not be a big deal. But in that case, it did look a little more complicated. So maybe in that, you're right. Maybe that explains why there's so little, that case looks so confusing, I guess, I could say. Good point. Thanks, Kyle.